Okay, the next chapter we're going to be learning about is chapter 4.5, Exponential Growth and Decay. One of the many applications of algebra is to predict the behavior of unknown events, is to predict the future. There's clearly no way to know exactly what's going to happen in the future, but based on patterns that occur in natural events, we can kind of predict, along the lines of what can we expect to happen. Now, a lot of things that happen in the natural world actually happen to model exponential growth and decay models. Now, exponential growth and decay models actually a lot of things. It has to do a lot with investments and banking, loans and savings accounts, etc. There's so many different applications. Population is the biggest one. What we're going to be doing in this chapter is we're going to be using what we've learned already about exponential and logarithmic functions these past couple of chapters. We're going to apply that to solve real-world application problems. Okay. So the first thing we're going to do is we're going to start with the function or model of exponential growth or decay. So the function model, well, I'm going to go ahead and I'll write it bigger right here because it's kind of small. It's f of t. I'll go ahead and write out to the side a little bit bigger. F of t equals a naught times e raised to the k times t power. Now this is the general model of an exponential function, and what I mean by that is if something's an exponential function, it'll kind of follow this same formula and function for the most part. Okay. Another way to write it is you can write the instead of f of t, you can also just write capital A. Same thing. You can write just capital A instead, which I actually will be doing, so I'll probably just write capital A instead. Okay. I also want to kind of know what each of these variables means, because right now it's just a bunch of letters. So out to the side, and I encourage you to do so as well, I'm going to write down what do each of these variables represent. The first variable that we see is this capital A. Now this capital A, I guess I'll write it right here. This capital A is the ending amount of something. Ending amount. Okay. A naught, that's how you would pronounce it. A, and it's like this little zero on the bottom. A naught, that's the starting amount, whether it be population or money or whatever they're talking about. That's the starting amount. That's how much are you starting with. The initial amount or principal amount. E, remember, E is not a variable. E is actually a number. It's a famous irrational number. It's about 2.71 and the decimals go on forever. It's a famous number, just like pi. Think of it as a number that was pi. That's there. We don't ever have to calculate E. Our calculator actually can help us calculate that for us. Second ln. And it's about 2.71 and the decimals go on forever. Even today, there's people still finding what's the millionth decimal to this number, or what's the next decimal to this number. So it continues on forever. It's an irrational number. We don't have to worry about ever calculating E because we already know the value of E. Okay. Next, you have this K value. Now K can be referred to as the growth or decay. Growth or decay factor. That's pretty much how much is this exponential function growing by or decaying by, and I'll tell you exactly how we know which one is happening. But K pretty much is this number that is going to tell us how much is the function growing by or decaying by. And the last variable that you see here is this variable T, and T is the time, and it's generally always in years. Okay, that has gone by. Now this is the formula for an exponential function, and this is what each of those variables mean. Now exponential functions can either grow or they can decrease over time. And there's an easy way to tell what's going to happen. If your K value, the K, whatever our K value is, if the K value is greater than 0, meaning if it's a positive number, you know that the function will grow over time. That's a plus sign. Okay. You don't even have to graph it. You can just say, hey, K is positive 3, so I know the function is going to increase over time. if the k value, whatever the k value they give you, is a number less than 0, meaning it's a negative number, you know the function's going to decrease over time. You don't even have to graph it. You can say, already I know that the function will decrease over time, whether it be population we're talking about or money, etc. That's an easy way to tell what type of exponential function you have, whether it be growth or decay. Let me go ahead and just write that. Growth, also called increasing, and this would be an exponential decay function, also called decreasing. Okay. All right, so I've gone over what an exponential function looks like, this formula, what do each of those variables mean, how to know if your function is going to grow or decay. And what we're going to do next, we're actually going to do an example of an application that involves exponential functions. So let's go ahead and start with example number 1. Like I said, the biggest application of exponential functions is population. A lot of times, population models almost a perfect exponential function. We're growing exponentially, which means we're growing at a super fast rate. So we're given a graph, this little bar chart, and it shows us the U.S. population between the years 1970, every 10 years until 2010. It says in the beginning, 1970, the population was 203.3 million. And by the year 2010, the population grew to 308.7 million. So the first part of this question is asking us, find an exponential growth function that models this data. Now when it says find an exponential growth function, it just means come up with a function using this model to represent this data. So I'm going to go ahead and start with A, and the goal is I want to come up with a growth function. I want to come up, what's the function to model this? Now I'm going to go ahead and copy down this formula that I have on top, because this is the formula that models exponential functions. And it tells us this is an exponential function. A naught times e to the k times t power. Now I don't actually have all of the values yet, but I can go ahead and plug in what I do know. So let's go ahead and see what we do know. The goal, remember, t is our variable. T is what changes time, whether it be 10 years, 20 years, 30 years. So that's our variable. So we do want to function with t as the variable in the end. But let's go ahead and see what we can plug in and what we can find out just by looking at our data. Now, like I said earlier, capital A is the ending amount. So if we're just looking at data between 1970 and 2010, what is the ending amount? Well, that would be the amount of people in 2010. So in 2010, there was 308.7 million people. So A, being my ending amount, is going to be 308.7 million. Now you can go ahead and write 308.7 million, but I'm going to go ahead and just leave it in this form instead of writing all those zeros, as long as I keep it consistent with both numbers that I plug in. All right, my A naught, remember A sub naught, that just means what's your starting amount. Well, if we're looking at the data between 1970 and 2010, the starting amount is how many people did you start off with in 1970. And in 1970, we started off with 203.3. Okay. E, remember, E is just an irrational number. You don't have to worry about calculating that. K is the growth factor. Now, I don't know what the growth factor is. It is growing, because see how the numbers are increasing. We don't know what that is. It doesn't tell us. So for now, I'm just going to leave it as K, because I don't know what that is yet. Okay. What about T? T is how much time in years has gone by. We can calculate that. We started with 1970. We went up until 2010. So between those two time frames, how many years have gone by? Well, 1970 to 2010, that's a total of 40 years. So my T value is 40. Okay, because 2010 minus 1970 is 40. Now, I have pretty much everything figured out. I just don't know what K is. So we pretty much, all we have to do now is solve for K. So I have an equation, and I'm going to do just that. So let's see. K is on the right side, so I'm going to start with the right-hand side. I want to get rid of everything else except for the k value. Okay. Now, we do want to get rid of the 40, we want to get rid of the e, we want to get rid of this 203. We're going to start with working on the outside and then work our way in. The thing on the outside is this 203.3. So we're going to start with getting rid of that. 203.3 is being multiplied by e to the k times 40. So the opposite of multiplication is division. So I'm going to go ahead and divide both sides by 203.3. And I have to divide the other side by 203.3. Okay. 203.3 divided by itself, that's just one whole, so those will cancel. And let's see, we have 308.7 divided by 203.3, and that is the decimal. So we're going to round. It's about 1.518, and I'm rounding, so I'm going to use these approximate symbols now. All I'm left with on the right-hand side is an e raised to the k times 40 power. Okay. All right, so I now want to get rid of, I want to get rid of the 40 and the e. But notice the k and the 40 are both in the exponent area. So before you can deal with this exponent, you have to get rid of this base e. Okay, we have to get rid of the base e. There's two ways to do this. You could convert it to log form. Right now it's an exponential, where you could convert it to log form, and it would be log base e of 1.518 equals k40, and that's fine. Another way, though, anytime you have the base e, because it's not e times k, it's e to the k power, so you can't divide by e. It's e to the k power. E is our base. Anytime you want to get rid of a base e, the opposite of e is natural log. So what we can do is we can take the natural log of both sides, and that'll cancel out. Natural log of e, those are inverse operations, just like addition and subtraction. These are inverse operations. And what we're going to have is those two will cancel out, and we're just left with natural log of 1.518, and I can calculate that using my calculator. Turn the brightness on this. You can see that. All right, natural log. And instead of rounding, what I like to do is I like to copy and paste it just so I don't round to the end. Natural log of that entire number. And I get about 0.41768, etc. 0.418 if I'm rounding that third decimal. But I like to keep this typed in and round at the very end. It's approximately, and the only thing I'm left with on the right hand side is a k times 40. Okay. I'm almost done. I'm trying to solve for k. So the only thing I need to get rid of now is this times 40. And we know how to get rid of multiplying by 40. We're just going to do the opposite of multiplication, which is division. So I'm going to divide both sides by 40. Times 40 divided by 40, those will cancel out. It's just one whole. And our k value is 0.418, pretty much this last number, divided by 40. See how I just kind of leave it typed in? And this way I only round at the very end. And there's our final answer. It is 0.01044. It doesn't tell us how many decimals to round to. So I'll go ahead and just round to 4 decimals. 0.4. Okay. But if it tells you how many decimals, you can follow that guideline. It didn't tell us here though. And there's our k value. Now, you can leave it as this, and that is totally fine. There's our k value. If you wanted to write this as a percentage, you could have also written it as, remember, take the decimal, move it 2 spots to the right to make it a percentage, and this would be 1.04%. Okay, it might ask for percentage, or it might ask for it as a regular number, either way, but those are both ways. Now, the question was not saying find the growth factor. It said find an exponential function. So even though that's not our final answer, it's pretty close. All we have to do is go back and just write our final equation. So our final function to model this is the ending amount equals the starting amount, which we said was 203.3 times e raised to the k. We do know what k is. We just figured that out. It's about 0.0104 times t power. And And there's our growth function. Okay. Now you might be wondering, well, we know what t is. I thought t was 40. Why didn't you plug in 40 for t? Or I thought capital A was 308.7. This is the growth function. We leave it in this form because this function will allow us to find the population for any years, not just up until 2010. Let's say I wanted to know what's the population going to be like in the year 2036. Well, I could use this function because I left t as a variable, and I could plug in the number of years that'll pass by since in 2036, and I can figure out what will be the ending amount there. So we like to have it in this form because this form allows you to find the population, the ending population, the ending amount, no matter what time and years you want to figure out. And that's why we like this form the best. As long as you know what k is, which we did, and the starting amount, and e is just this number, a rational number, you have a function. And there's our answer. Okay. All right, so we know the function, and then part B says, by which year will the U.S. population reach 335 million? Okay, so I didn't leave too much space for this. Let me go ahead and make a space for it. Go ahead and write it right here. All right, this will be part B. Okay. All right, by which year will the U.S. population reach 335 million? Now, again, I do want to start with pretty much my function that we've already come up with, and we're trying to figure out by what year. So we are trying to figure out time. We don't know what time is in this case. How much time is going to have to pass by for our population to reach 335 million? Now remember, capital A, like I said earlier, is the ending amount. So pretty much what they're asking is, when will your capital A or ending amount be 335 million? Well, we don't know, but we can plug in 335 million for capital A, because that's what we want the ending amount to be. Well, that's what the question's asking. Equals, everything else that stays the same. The starting amount is still 203.3. E, the growth factor doesn't change. It's still 0.0104. And we don't know what t is. That's what we're trying to figure out. How much time, by what year, is this going to be our ending amount? Okay. So we have everything. All we have to do is solve for t. So kind of similar to the last part. I'm trying to solve for t, so my first step is to start with the side that e is on, which is this right-hand side. I want to get rid of everything else except the e, so work your way on the outside and then in. The thing on the outside is this 203.3 that's being multiplied by e. So I'm going to divide both sides by 203.3 to get rid of it. 203.3 divided by itself cancels out. I'm left with 335 divided by 203.3, which I can calculate that on my calculator. It's a decimal, but that's fine. We can just round on paper for now and just leave that typed in. It's about 1.648 approximately. And all I'm left with on the right-hand side is e to the 0.0104 t power. We're trying to solve for t. All right, I do want to get rid of this 0.0104, but I also want to get rid of this base e. Now remember, this is a base e. It's not e times 0.014t. It's e to this power. And so you have two options. You could convert it to log form, which we covered last couple of chapters. Or the opposite, if you ever want to get rid of a base e, is just to take the natural log of both sides, the ln. I ran out of space there, but that says ln. And you have to take the natural log of the other side as well. Okay. And what that does is natural log and e are inverse operations. They undo each other. So essentially, those just cancel each other out. And all we have left is natural log of 1.648, which I can calculate. Natural log of, and instead of typing it, I'm just going to copy and paste that last answer. And that's what I got. 0.499. I'm rounding on paper, but I'm just going to leave it typed into my calculator, is approximately, and the only thing I have left on the right-hand side is 0.0104t. Okay. I'm almost done. I just want to figure out what t is. So all I have to do is get rid of this 0.0104 that's being multiplied by t. And the opposite of multiplication is division. So I'm going to divide both sides by 0.0104. 0.0104. Those will cancel each other out. And our answer will be 0.499, which is pretty much this last answer, divided by 0.0104. And there is our t value, which is 48.02. If I'm writing that third decimal, I'll just do 0.24. And this is how many years. This is, remember, t is time in years. Okay. So the question says by which year? Well, technically, this is not the answer. We just said 48 years will have to occur before our population reaches 335 million. If you wanted to know the actual year, what year is it when this happens, you would just take your starting year, which is 1970, and add, 1970, and add 48.024 years, and it would be the year 2018. I mean, a little after because there's some decimals, but it would be the year 2018-ish. So, AKA, this would be the year would be 2018 when the U.S. population is 335 million. Okay. And there's our answer. This definitely takes a lot of practice knowing how to deal with exponential functions and solving. That's the biggest thing. If you can set it up, great. But the biggest thing that I think a lot of students struggle with is solving. How do we solve for k, or how do we solve for t? How do we get rid of e and natural logs, etc.? So I encourage you to just do a couple more practice problems if you're having trouble with that, because that's the biggest issue that students run into. We're going to do a couple more examples to get you some more practice in case that didn't make too much sense. Okay, so here we go. All right, and I tried to take these example problems straight from your homework on my math lab, so they should be very similar to the problems that you're going to be seeing. Okay. All right, example number 2. This is a population growth model. It's going to be growing. It tells you right there. And all it says is to complete the table for this population growth model of a certain country. Okay. I didn't write it, but this does model exponential functions. Okay. So we know what the population in 2002 is of some country. We want to know what the population in 2021 will be. And they also tell us what the growth rate is. How fast is it growing? Now, this is an exponential function. I should have written that in there, but I didn't. So we know we're going to be using the exponential growth model formula, which is right here. And I'm going to go ahead and write that again at the top of this example. And that is A equals A naught times E raised to the k times t power. Okay, and we know what each of those variables means. I wrote them down over here. All right, I'm trying to figure out what's going to be the population in the year 2021. What's the ending population? Well, remember, capital A is the ending population or ending amount. We don't know what the ending population will be in 2021, so I'm going to leave it as a capital A because we don't know what that is. A naught is the starting population. We do know what the starting population is. That's the population in the year they give you to start off with, which is 2002. And so the starting population will be 23.1 million. Okay. E is just an irrational number, so you don't have to worry about trying to figure out what is E. The K is the growth factor, which they also tell us is 0.0213. And T is how much time in years are going to occur. Time in years are going to pass by to get to your ending amount. Well, it doesn't say specifically, but it tells you the years. It says the starting year, if we're starting with the year 2002, and we want you to find the ending year population of 2021, you can calculate how many years have gone by between the 2 years. So if we just subtract the 2 years, the year 2021 minus the starting year of 2002, all you have to do is figure out what's 2021 minus 2002, and you will get 19. So 19 years is our t value. So instead of t, I'm going to plug in the number 19. Okay. And all I have to do now is just calculate that. I can use my calculator because it'd be hard to do that without one. I'm going to type all that in. 23.1 times e raised to the 0.0213 times 19. Make sure that the 19 is also in the exponent area. And I got 34.62, I'm just going to round to 3 decimals, 623. Remember, this is in millions. And that's how many people we predict will be in the population in the year 2021. And there's our answer. So we didn't have to solve for t using algebra. We just had to plug in some numbers and calculate. Okay, as long as you know what number are you plugging in, you can kind of, once you get there, it'll be pretty simple from there. All right. And you can even write that in. 34.623 million. Okay, awesome. All right, another example, very similar. It says complete the table below for the population growth model of a certain country. And I didn't write it in here, but this is an exponential growth model. So we will be using the exponential growth model formula, which is right here. I'm going to write it down again. It's A equals A naught times e raised to the k times t power. All right, I want to figure out what is the growth rate. So we don't know what k is. That's what we're going to be solving for. All right, remember, A is the ending amount. So the ending amount of people, we're talking about people, population. The ending amount of people, well, is the one that's later on, which is 2021 year. So in the year 2021, there is 65,120. So that's going to be my ending amount of people, 65,120. A sub naught is the starting amount of people. Well, we're starting with the year 2002, so the number of people in 2002 is 56,300. So that's going to be A naught. E is just an irrational number. K, we don't know what K is. That's what is empty. And then T is the time in years that have gone by. Now, it doesn't tell us specifically, but it tells you the two time years. So the time in years is just take the 2 years and subtract them. So all I'm going to do is take the ending year, which is 2021, minus the year 2002. And once again, we get the same answer as before, 19 years. So my t value is 19. Okay. All right, we know everything but k. That's the only thing we don't know. So all I'm going to do is I'm going to solve for k. I'm going to get rid of everything else but k. So I'm going to start with the right-hand side because that's where k is at. I do want to get rid of everything else. Always start with anything on the outside and then work your way in. The thing on the outside is this 56,300, which is being multiplied by e. So the opposite of multiplication is division. So I'm going to divide both sides by 56,300. I'm going to divide the other side by 56,300. 56,300 divided by itself cancels out. That's just one whole. And I have 65,120 divided by 56,300. And I got some decimal 1.15, sorry, 66, I'm just going to round to 3 decimal places for now, is approximately, and the only thing I'm left with on the right hand side is e raised to the k times 19 power. Alright, I want to get rid of this base e. This is not e being multiplied, it's e raised to the power of k times 19. You can convert this to log form, or another way to do it, and I think it's more simpler, is anytime you want to get rid of a base e, the inverse operation is just natural log. So I can take the natural log as long as I do it to both sides of the equation. And what that does, it cancels out. Natural log of e, their inverse operation, so essentially it just cancels out. And all we're left with is natural log of 1.157, which I can type that in actually, darn it, I didn't want to round to the very end, so let me go ahead and type in that last number that I had, and I erased it. Okay, natural log of, I'm just going to copy and paste that, and that's what I got, 0.14, and I'm going to just round it to 6 on paper. K times 19 is the only thing I'm left with on the right hand side. Okay. Alright, I'm almost done. I'm trying to figure out what K is. So the only thing I need to do is get rid of this times 19 by dividing both sides by 19. Okay. 19 divided by 19 is 1 whole, so those cancel out. And our K value is approximately, well, I'm going to just divide these two numbers. So just pretty much that last number divided by 19. And I got 0.00777 if I'm rounding to 4 decimal places, because it's 6.5 and 5 makes it that 6 go up to 7. And there's our K value. So I can go ahead and put that in 0.0077, or sometimes if you want to write it as a percentage, you just move the decimal 2 spots over and you can write it as a percentage. 7.7%. That means it's growing, population is growing by about 7.7% every year. Okay. Alright. Alright, we're going to go ahead and do one more example. So we just did a couple examples of exponential growth and decay using the exponential model. Okay. And then the last example, example number 4, we are going to be modeling the spread of flu with something called a logistic growth model. Okay. Now, logistic growth models are pretty much anything in this form. If you're given a function and it's in this form, it's called a logistic growth model. It just means that it's growing with the model of a logarithm. And again, this is another natural phenomenon that kind of models things in natural events, such as the flu being one of them. So we're given this function, f of t is equal to 30,000 divided by 1 plus 20 times e to the negative 1.5t. Now, e is just some irrational number. We don't have to solve for that. Remember, t, I'll write this down, t is just the time in years that have gone by. Okay, and f of t, that's just like our ending amount, whatever we're talking about. Okay, and it even says f of t is the number of people who have become ill with influenza. So f of t is how many people have become sick with the flu, and t, oh I'm sorry I messed up, is t is weeks in this case. They even tell us t is going to represent weeks. So T is going to be how much time has gone by in weeks after the initial breakout in a town with 30,000 inhabitants. So very similar to actually the pandemic that's going on right now. Things like that this is how scientists kind of predict how many people are going to be sick with the flu or whatever virus in this many weeks or this many months, etc. Okay. So the first question of this says, how many people became ill with the flu when the epidemic began? Now this model tells us, remember, f of t is how many people have become sick. So how many people, number of ill people with the flu. Okay. So if it says how many people have become sick with the flu just when the epidemic began. Well, if the epidemic is just beginning, at the very beginning, no time has gone by. So if we're trying to figure out how many people are ill with the flu at the very beginning, well then the t would be 0, because if it's just beginning, there's no weeks that have gone by. This is the very beginning. So in order to find out what is the number of people that are sick with the flu at the beginning, you're just going to take this function, 30,000, divided by 1 plus 20 times e raised to the negative 1.5, and instead of t, well, t is going to be 0 because it just began. No time has gone by yet. We're just trying to figure out how many people are sick just when it's beginning and no time has gone by. And I can type this whole thing into my calculator, I encourage you to use the fraction template. On the numerator will be 30,000. There you go. On the denominator will be 1 plus 20 raised to 1 plus 20 times e raised to the negative 1.5 times 0 power. And this is what I got. I got 1,428, about 0.57 if we're rounding. And this is people, so this is how many people are sick with the flu just when the epidemic is beginning. Ill people at beginning of pandemic. Okay. All right. Question number B is asking, how many people were ill by the end of the 4th week? So in this case, we're trying to figure out how many people are ill, so we're still trying to figure out what is f of t. It's going to equal 30,000 divided by 1 plus 20 times e. I'm just copying down this formula to the negative 1.5. And for our t value, well, it's saying how many people will be sick at the end of 4 weeks. And remember, t is a time in weeks. Well, if we're talking about 4 weeks, my t value will be 4. And let's go ahead and we can type that entire thing in. I'm actually just going to copy and paste it so I don't have to retype the whole thing. I'm just going to change that 0 to a 4. And that's what I got. This is 28,000, holy cow, 582 point, if I'm rounding, actually 0.99, I'll round to 3 decimals in this case, 0.997 ill people. So that's how many people now have the flu at just 4 weeks. Just crazy to see how fast things like this grow. Okay. All right. Part says, what is the limiting size of the population that becomes ill? Now, this isn't really a calculation problem. This is more of like something that you just need to consider and think about what makes sense. According to this model and everything they've told us, what is the limiting size? Meaning, what is the most amount of people? What's the maximum amount of people of this population that can become ill? We can use this model to predict how many people will be sick at the beginning, after 4 weeks, after 5 weeks, 6 weeks, etc. But if we're just, talking about a specific one town, it's not going to go on forever. Eventually, they're going to run out of people to get sick. So if you look at this model, what was the population of the town that we're talking about? It was 30,000 people. So, realistically, this model can't go on forever for infinity weeks. Eventually, it's going to run out of people to get sick. And so, realistically, the limiting or maximum size of people that can become sick is 30,000. So, the limiting size of people or population that can get sick with the flu is 30,000, because there's no more than 30,000 people in the town. And after 4 weeks, 28,000 of them were already sick, so not much longer. This can't go on for much longer than 4 or 5 weeks, and eventually you're already at the maximum of people that can get sick. Okay. And that's all there was for part C. And then last part D, according to this same model that we've been working with, when will the number of ill people become 3,000? Okay, so in this case, you're not trying to figure out the ending amount. It says, when will the number of ill people, which is f of t, be 3,000? So we're going to use this model, and instead of f of t, it tells us when will f of t, the ill people, be 3,000. So I'm going to plug in the number 3,000 for f of t. So it'll be 3,000 people is equal to 30,000, and everything else stays the same. 1 plus 20, just copying this down, times e to the negative 1.5 times t power. Okay. So what I've done is we're trying to figure out now When will this happen? How many weeks are going to go by when 3,000 people will be sick? Okay, I know it's going to be after the beginning because this is only 1,000. I know it'll be before 4 weeks, so that's already up to almost 28,000. So somewhere in between there, I know, is when it's going to happen. But to figure out the exact answer, we're going to actually have to solve for t. Now this one is probably something we haven't really seen before. We have to solve for t, and it's already in the denominator. So there's a couple of different ways to do this. Some people you can make this a fraction by putting it over 1. And you can cross multiply, maybe do it that way. There's many ways to go about this, so if you have a different way, that's totally fine. I'm going to go ahead and just solve for it, getting rid of the fraction. So I do want to get rid of this fraction. I know t's there on the bottom, and I do want to solve for t, but I want to get rid of the fraction. I want to get it out of the fraction. And so fractions, remember, are just division. So what I'm going to do is I'm going to multiply this whole side, because 30,000 is being divided by this whole denominator. So I'm going to multiply 30,000 by that whole denominator, because the opposite of division is multiplication. And whatever I do to one side, I have to do to the other side. So I'm going to multiply the other side by the same thing. 1 plus 20 times e to the negative 1.5t. And I know I'm running out of space, but I'll try my best. Okay? And the reason I did that is because 30,000 times this value and 30,000 divided by this value, those will cancel each other out, because I'm multiplying and dividing by the same thing, and that just cancels out. It's one whole. And what I'm left with now, let's see if I have room to write it, is 30,000 times this whole thing. And you can write it in whatever order you want. Or sorry, 3,000. 3,000 times this whole thing. I'm just going to leave it in parentheses. 1 plus 20 times e to negative 1.5t equals, and all I have on the right hand side is 30,000. Okay. Alright, I am trying to solve for t. Some people might opt to distribute, and that's fine if you want to do that. I'm trying to solve for t, so instead I'm just going to get rid of this 3,000 that's being multiplied by all this, and I'm going to divide by 3,000 on both sides. This one is a bit of a challenge one, I will say that one. That's why I'm ending with it. Okay. And 3,000 divided by itself, those cancel out. It's just one whole. And I'm going to write out here to the side. I am now left with, I'm just left with 1 plus 20 times e to the negative 1.5t is equal to 30,000 divided by 3,000. You can use your calculator if you need to, but I already know that's just 10. Okay. I'm solving for t. So I'm just going to start with this left-hand side. I'm going to subtract 1 from both sides. 1 minus 1, those cancel out. I'm left with 20 times e to the negative 1.5t. 10 minus 1 is 9. Okay. I'm going to get rid of this 20 next. 20 is being multiplied by e to the negative 1.5, so I'm going to just divide both sides by 20. 20 divided by itself cancels. And I'm now left with, I'm going to write it up here, e to the negative 1.5t equals 9 divided by 20. You can leave it as a fraction if you want. You can go ahead and write it as a decimal. 9 divided by 20 is 0.45. Okay. And I do want to get rid of e. Remember, this is a base e, so anytime you want to get rid of a base e, you can convert it to log form, or you can just take the natural log of both sides. Okay. And natural log of e, they cancel each other out. Those are inverse operations. And I'm just left with negative 1.5 times t is equal to natural log of 0.45, which is this whole decimal, negative, and I'm rounding, so I did approximate symbols, 0.799, if I'm rounding that third decimal. I'm almost done. I just need to get rid of this negative 1.5 that's being multiplied by t by dividing by negative 1.5. And those cancel out with each other, and t is approximately negative 0.798 divided by negative 1.5, and I got 0.5323. And remember, T is given to us in weeks. So basically what this says is that not even just a little over half of a week, that's when 3,000 people will be sick already. It's just after half of a week, or 0.5 weeks. That's how long it's going to take for 3,000 people to get sick with the flu. Okay. Again, that last part was a challenge one. I think there's just one on your homework similar to that, so I wanted to do at least one like that. Okay. All right, and that is it.